We're now going to talk about another example that's going to demonstrate some of the quirks of Java streams and parallel streams. And actually, this is an example that Sanjeev will recognize because he pointed this strange behavior out to me a couple of years ago. And together we wrote a test program to demonstrate it. So this is going to show why certain Java stream operations like iterate and limit perform very poorly in the context of Java parallel streams. So here's the example we're going to do. We're going to go ahead and demonstrate the performance of using the iterate and limit method with a sequential stream and a parallel stream. And then we're going to go ahead and give the same behavior, except we're going to use the range operation. So let's go ahead and take a look at this. I think I'll show you the code first, and then we'll run the example. So it turns out that certain operations on parallel streams are inherently inefficient, even though they kind of work by some definition of work, even though they run and give you the right results. They're incredibly inefficient. So what we're trying to do here is we're writing a little piece of code that will compute the square root of the first n even numbers. And we're going to toggle on sequential and parallel streams. So actually, let me go ahead and run the program first, and you can kind of see the behavior here. So the parallel stream version of this stuff, as you can see, took 535 milliseconds to find the square root of the first, looks like 1 million even numbers. And the sequential version of the same code took literally half the time. So not only are we not getting a speed up with parallel streams in this case, we're getting a massive slowdown, a 2x slowdown. When we do the same computation that delivers the same results with int stream range, then it also performs differently here as well. I'm going to run that again just to make sure that we're not getting weird results from timing. Yeah, so you can see here that in both cases, the version that was sequential is actually giving us a win, which is kind of unusual. But the reason, again, has to do with the overhead. I think if I crank the numbers up even higher, we'd eventually start to get a win from parallel streams, maybe. So let's go ahead and take a look at the code. But you can certainly see that the int stream range is not nearly as bad as the iterate version. So let's take a look at the code. So this code is going to start with the value 2, and it's going to iterate, and every time we do something, it's going to take the value and add 1 to it. So it's going to go, 2, 3, 4, 5, 6, etc., forever. That's what the iterate method does. And then we can toggle on if it runs in parallel or not. What we then do is we go ahead and basically get rid of all the odd numbers. So we only keep the even numbers around. And then we're going to limit the number of elements to the number that we give here, which is 1 million or whatever. And then once we've limited it to the number of things we want to take, we then go ahead and find the square root of all those numbers. They should all be even numbers. And we collect them into a list. So we have a list of doubles. And then we go ahead and basically figure out how long it took to do that. And as you can see, the performance is abysmally bad. Just for kicks, let me see if I can make, let's do 10 million of these things and see if we ever do get a win from using parallel streams, from parallelism at all. This is a classic example of how some things just take a while to pay off. So I'm going to let that run in the background because it's going to take a while to run. Hopefully it won't make my machine stop working. So that was the iterative version. And it turns out that the iterate method with parallel streams is just inherently inefficient because of the semantics of how parallel streams have to work. And limit doesn't help things either. So here's how to do this code with same algorithm or same behavior, same output, but much more efficient. So what we're going to do here is we're going to use long stream, and we're going to start at the value 2, and we're going to go to the number times 2 plus 1. So this has got a bounded range, which makes it much easier to do a parallel split iterator on this. Again, we go ahead and split things up to either be parallel or sequential, and then we go through and get rid of all the odd numbers, compute the square root of everything that's left of the even numbers, and collect them into a list. And we compute how long it took to do all that stuff. So let's see if in the meantime our program is stopped. Well, it looks like we ran out of memory. Guess we'll have to kind of crank that back a little bit. like might be just a touch too much to go with 10 million. Let's try, I don't know, 2 million of them, see if that works. This particular computer I'm working on today only has 16 gigabytes of memory. My main computer has 64 gigabytes of memory. So you can see here, at long last, we get the numbers big enough, and parallel streams finally start to be a win. But you'll notice that the parallel stream for iterate is even worse. So the bigger the n, the worse it gets. So the key point here that I want to get across in this lesson is the fact that using certain kinds of operations in a stream can make them perform very poorly. Let's see if we have any questions. We have a question. Let's see, where did that go? In the n times q model, do we need to use some tool to compute q? You could use a profiler to figure out what the average time is. There's various ways to do this. Basically, the easy way to do it, if you don't want to spend a lot of time trying to calculate q in some precise way, is just ask yourself, do I touch the data a lot that I'm processing? And if the answer is no, then q is probably very low. If the answer is yes, if you transform it, if you do things like square root or finding if it's a prime number, all that good stuff, then it, of course, will have, q will be higher. N times q is just a heuristic. And the most important thing is n. So as you just saw with the example we looked at, when n gets very large, as we saw with 2 million elements, then parallelism starts to be a win, assuming you're choosing the right operations in this case. Okay, let's see. There's another question here. Did you say the main thread is not necessarily involved in the case of completable future, but is involved in parallel stream? Yes, that's correct, because with the parallel stream version, typically the calling thread, let's not call it the main thread, let's call it the calling thread, because that's the thread that matters. The calling thread is always going to be blocked in some kind of terminal operation. So it'll be a terminal operation, something like for each, or collect, or reduce. So in that case, the calling thread, not necessarily the main thread, the calling thread can be used and pitch in to do the processing. With completable futures, however, the whole point is not to block the main thread, not to block the calling thread. So of course, it couldn't possibly be used by default in the computations because the whole point is not to block the caller. So therefore, in that case, you're only going to maybe pitch in if you call join. And I'd have to go look at the code to see if it pitches in. It may or may not. But the key point there is that with parallel streams, you have a terminal operation that guarantees that you're stuck there, the calling thread is stuck, whereas for the other operations on completable future, you're deliberately trying not to block the calling thread. Let's see. I assume that the threshold of splitting tasks is too small, something like one array box. Is there a way to increase the threshold? Yeah, that's a great question. So by default, the built-in collections, the predefined collections like array list and so on, those things will split right down to one element. And that could indeed be too fine-grained. If you don't like that behavior, the way to fix that is to subclass from array list or make your own list, and then go ahead and re-implement how you want the splitterators to behave. Because ultimately, whatever comes back from the splitterator factor method called by the stream support.stream are called and passed by the parallel stream method to stream support.stream, that's what's going to dictate the behavior. So you can define your own splitterators if things get too fine-grained. I've actually done that in some situations for good reason, but not on the built-in collections. But there's no reason you couldn't. You could just go ahead and subclass from array list and then redefine the splitterator if you so chose to do that. Yeah, that's a very interesting question. So the other question is just confirming parallel streams. So let me show you. So the question here is, does the calling thread block in a parallel stream? And as you'll see here in a second, the answer has absolutely got to be yes, as you'll note in just a second. Because if you look at this code, anywhere we see stream code, you can see that we always end up calling a terminal operation at the end of the stream. In fact, in an earlier session, I pointed out if you omit the terminal operation, nothing gets done at all. So you're always calling a terminal operation with a stream, parallel stream, sequential stream, and that terminal operation is always going to block because it can't make any further progress until it finishes and collects the data or does the reduction or finishes doing the for each operation. So those things will always end up basically completing. Okay, so that's the end of this example.